Hello.
Hello.
Hi. Hi. Hi,
Hello,
Sandra.
hi.
Hey, Alan.
Hi. How
I
is
see.
everyone?
Hello,
Good.
Alan, Nadia.
All good here. How's everything there?
Very good.
Good.
You're
The
in San
US is
Fran.
playing at noon, so we are all hyped
Okay.
for soccer.
Are you in San Francisco now, Alan?
Yes, there's Alcatraz right here.
Wow, that's nice. I'm still bummed I didn't get a chance to visit you there.
Yeah, you have to come back. It's not so nice now because it's the foggy time, so it never really clears up until
Mm,
maybe late in the afternoon.
I'm
But
sure it's nice enough. You become very selective when you're so spoiled.
For some reason, the way I set up the system, I had to manually admit you to the meeting, which is kind of strange. If I had
Yeah.
to admit everyone manually, it's going to be. I need to find
Is,
a way next time so it just automatically admits people.
so, Mattia,
yeah.
how many people are you? Do you know how many people are usually attending this live? I
I
assume a lot of people are watching the recording, probably.
Very possibly. Yeah, certainly that. The majority bulk of visibility is going to be there. I don't know because it's the first time I attended one previously, but yeah, I don't remember exactly the number.
It was well attended in the past. I don't know now.
Yeah, let's hope. We did our best to advertise. This is the first one of the series, right? Maybe it's gonna have a little bit of initiation, but that should be. I spread it around as much as I could.
Yeah, last time, let's look. I did one in 2021, 5 years ago. So how is BioX doing, Alan? Now we have time
Oh,
to
good.
chat.
Yeah, it's summer now. I've had a week of summer, and
Is
everything
that
is kind of like getting.
is, is the term over?
Yeah,
Oh, that's what you mean by summer.
yeah. Summer is like
Yeah,
summer water,
yeah,
like nothing to do.
yeah, that's
It's nice.
great.
Yeah. So we are all winding down.
Hmm.
We had graduation this Sunday, but I didn't go. And now everything is quiet on campus again, as you know.
Mm.
So yeah, it's nice.
You
Um,
still doing a lot of food?
yeah, we're doing food. We should do some more food together. Food is fun. We're having the burger thing and also
We have to do the
cheese and all kinds of
remember, we have to do the pancakes.
the pancakes.
Pancakes
Yes,
and crepe.
exactly. How about you?
Um, Yeah, I'm not doing food, though I said I might do a couple public lectures, one on food and one on drinks at some point. So that
Drinks,
should.
yeah.
Uh,
The big thing in the US is that the Scottish soccer fans drank all the beer in Boston.
there is no beer left.
No, for real not. So Scotland played in Boston, and then the beer
Yeah,
in the entire city, even gas stations, all the beer was gone. So it was on
yeah,
all the news. So that's a drink you can explore. People have said, so we've done this AI for burgers, right? And then a lot of people said you should use it to make wine. So that would actually
mm.
be interesting.
Yeah. So I've looked at wine and or how you quantify wine and all that. There's interesting things you can do there. Uh, to do. I don't know how you get to a certain place, but just as the number of properties you can identify for wine is interesting.
But not all mechanics. There's a lot of chemistry, probably, right?
Well, the problem it's liquid, right? So there's very little mechanics. except if you count pressing the grapes. So the new generation, the whatever they called, now they drink a lot of orange wine.
No, I don't know.
We only had
Grapes.
well, we only had red, white, and rosé, right, in the old days. But now you do orange, and so the red wine you get with grapes and the skin, and rosé you get with the. I think you get or do you get rosé? You get the juice, but not the skin, and the white you get white grapes, and I think the orange, which really looks orange, is white grapes with the skin or something like that. So you
Yeah,
have different combination giving you different
I've never
colors.
heard of orange. Okay, so that's
Yeah, so
interesting.
orange wine, and it's very orange. So that's why it's the new thing. That's well, it has existed for a while, but it's in fashion now.
Okay, I'll look for it. And have you tried it?
Yeah, it's
No.
great. I think I've tried it a few years ago in college, but I don't know enough about wine to tell you.
So Sip is at Oxford for 1 more week.
Oh, cool.
So we've been following all the Oxford pub history. And he's apparently spending more time in like pubs and things than
Did he go to
at.
the oldest pub? I think it's the Bear or something like that, the oldest one.
We'll ask him.
And you can go to the Eagle and Child, the one from Tolkien.
Oh, that's closed.
Yeah, they're redoing it. It might not be closed, but
It's
the one opposite is what
it's Lamb and Flag.
the Lamb and Flag. Yes, that's
Okay, now we
also.
have the expert. Hi, Henry.
That's why I'm here.
Maybe
Hey,
that's what we should
Michelle.
talk about.
Hi.
Hi, Michel.
Hey everyone, can you hear me?
Yeah,
Oh,
yeah.
We can
Okay.
hear you.
I just saw Michelle in Trieste, so we hung out there and had a lot of gelato and pizza,
and
Oh,
coffee.
nice.
coffee.
Very good.
Maybe we could start with with a little bit of introduction and bio of Alain. Alain, what do you think?
Yeah, yeah. I
Uh,
mean, when
I,
you before the talk, right? Or what you
Before,
mean?
yeah, as an introduction to the talk, we have like
Yeah. Of
20,
course.
20 minutes. Yeah.
well, if you ask me what I think I'm happy to give a talk. You can do all the
Mhm.
pre-talk that you
I will
want.
do all the embarrassing things of
Yeah,
you,
if
and then
given a
you have
choice,
1 hour to
given a
repair it.
choice, I would go straight into it. So, but
And
maybe
then you have
I'm
one
not given
hour
a
to make
choice.
up for it. Yeah, exactly.
Okay. So Alain, you're giving the talk, and then there's going to be like a
Open
round
discussion, I
table
think.
panel discussion.
Yeah,
But people from the audience can also ask questions.
yeah, of course.
Okay.
I see you have good books on your shelf, Michel.
Yeah, I have your book somewhere.
Yeah, I see it right there, the little one.
Oh yes, of course, of course. I
And you have
see you.
seashells. You have seashells.
She says, yeah, you gave it to me.
Oh, okay. Yeah, it
You,
looked like one of my.
you did a 3D printing.
Yeah, it's fun to do 3D printing, but then you get like, as you can see, tons of plastic crap everywhere, and then
True.
you never have enough space on your shelf and stuff. And I printed so many of these to do because I wanted to make
Oh
sure that
yes,
they
yes.
actually tie space.
Very good. I guess you could do like a guide and fill up a vertical wall.
Yeah, that'd be good.
Yeah. Very
Well,
nice.
actually, yeah, if I can show you, I won't have time to do it, but we had a project with people in. Let me show you uh, this one, so we can do a try. You see this?
Yeah. Oh, you did a wall.
Well, this is It's not a
Or it's
real one.
existing?
It's a virtual. It is a study by architects friend of mine who work in San Francisco at the California College of the Arts, and they took this shape and look at the properties, both mechanical but also as to do architecture, and to do
Right.
their various proposal with that. It's quite nice. I kind of like it. So yeah, and they did the blocks made out of eggshell and bacteria mixed to make them stick, so completely organic. So they went around San Francisco and asked for eggshells from diners to do, the place that do breakfast. And then they
Right.
cleaned them and ground them and then mixed with Bacillus subtilis and made a mold and cast them. And they do these little bricks. And they're very nice properties too, compared to rectangular ones.
So, but that photo on the right with the person walking, that was
Yeah, that's a
virtual.
mock-up, but the
Okay.
the little blocks are real. They actually made them and so on.
Right. Why eggshells?
Well, because it's a byproduct of food industry that's never been used. They wanted to do
Okay.
something organic, to recycle. And also, it's very good. It's very good material for building because it has the nice
Yes.
properties.
Very strong. But yeah, but in the US, the eggshells are washed, so maybe they lose some of their properties.
Yeah, but that's a very small organic layers that's lost, I think. That's why you have to keep them in the fridge.
Yes. Excellent.
Mm.
Well, I prepared a couple of questions. You want to know them in advance, or you want the?
Yeah, you're welcome to share. I'll have the whole time. As long as you're not going to try to convince me that the regular tetrahedron can tile the space.
Oh yeah, that's true.
I gave a short version of this talk in Trieste on Monday, and it was the strangest thing. A guy in the back, a physicist doing I don't know what. I said a very basic fact that the regular tetrahedron cannot tile space, and he wouldn't admit it. It would come up and keep arguing that, in his opinion, and that was like in physics textbook, supposedly, the regular tetrahedron tiles space. It's like, a three-line proof, and I was trying to understand what he was, if I'd done something wrong, if he had misunderstood what I was saying, trying to ask him what does he think and all. It took us like 5 minutes. I think he just wanted to give me a hard time, but it was a very bizarre experience, I have to say.
Could it be that he
Oh,
mixed up with the triangle?
Yeah, I mean, that's the same, right? And so the proof is like
Well,
really
you can tie the plane with a triangle.
Yeah, it's not that different from the triangle. It's the condition at the vertex, right? Instead of you have to
Yeah.
do it in space and
But in
define
2D it
correctly
works.
the angle. But yeah, that was bizarre. It got me completely flustered for the rest of the talk. I was wondering what was the point he was trying to make.
no, you didn't look frustrated. Don't worry. You were back on track.
No, and I said, was I too dismissive in some way? I wanted to make sure he understood. I think he wasn't doing in good faith either. Anyway,
I don't know. He didn't seem to know. He didn't seem to know a lot about solid state physics for sure.
yeah, but he said you prove. I have a counterexample. It's in the first chapter of a textbook in
That's
solid
true.
state physics. I
That's
said, what? That's not an argument.
Oh, there is Davide. He was at the talk too.
Yeah,
Ciao,
Davide
Davide.
was at
Yes,
the top.
nice to see you all.
Nice to see you again,
Meet
Davide.
you again. Actually, we met 2 days ago, but
Yeah, we
that's
had coffee yeah, was it yesterday? No, 2 days ago. We had coffee in the morning.
True.
Alain, this is Jimmy Xia from Singapore. Actually, so good to see you again. And thank you very much for being the first EML webinar speaker for the new season. Let's
For
call
the
it.
readout. Well, thank you very much for the invitation. It's a great honor.
Yeah. You actually gave an EML webinar. Was it 4 years ago, 5 years
I
ago?
think I just just check. It was almost 5 years ago now. Yeah.
Almost 5 years ago. Wow. Okay, time flies.
I can't even remember what it was about, but yeah, it was good. I think it's a very good format, by the way. I usually say no to about every kind of online seminar. I feel it's very depressing. But this is one of the few formats I think that actually work.
Yeah. Mm.
Yeah,
So
I do have
Mattia
this.
is now in charge of the webinar series. So it's certainly very difficult to refuse any request from Mattia. Mm. Alan, by the way, thank you very much for being the discussion leader.
Yeah, thank you. Thanks for inviting me. This is exciting. I actually like Alain said, I like the format of easily like talking in and then recording it. I'm sure a lot of people will watch the recording later.
Yeah. We have statistics of how many people watch the recordings. It's a huge number. I don't
Yeah, I
recall.
bet.
Yeah. Yeah. Good.
Yeah, that's great because if you think about well, especially after COVID or during COVID, the number of talks that are recorded and put online and that nobody watches, it's huge. The number of YouTube. Sometimes I find a talk that looks interesting and I look at how many views, it's like 13 views or something like that, You really need the exposure. You need to have a good system so that people know to find it. And
Yeah.
hey, Sébastien,
Hey, hello.
haven't seen you in a while. I'll be in Paris, Sébastien, in September. We should get together. I'll be there for the week.
Very nice. But tell
Okay,
me which week?
let me find out. Okay, September. I'll be visiting Roberto Toro, and it's the week of the 21st.
Let me see.
21st to 24th or 25th, something like that.
Okay, I'll put a note.
Okay. Be great to see you.
Yeah.
Oh, John McLaughlin. A sighting. I went all the way to Stockholm to see you, and I didn't.
I'm sorry about that, but I understand since I missed that talk, I'll learn similar things today.
Yeah, it's the same talk, so.
Oh, good.
Well, updated version, upgraded.
Tainted love. Tainted love.
Tainted love, yeah.
That's tough. So, how is Zakai?
Zakai is doing okay, I think.
Yeah.
Yeah, so I was in Berkeley for a month, and I managed to not to miss Ellen for one reason or another. It was either one thing or the other. Yeah, it's completely. I'm really still annoyed by that. But yeah, so I went and spent some time there, the Miller Institute, which was very nice, and spent some time with Zakai, which was also nice. Yeah, Zakai is doing well.
Has he made the transition from formal logic to something else, or?
I never exactly know, but yeah, he's going to more philosophy than logic, analytical philosophy, I think it's called.
What?
It took them all that time to realize that logic is a little dry, or too abstract, or too formal, or too difficult, or too, yeah.
So on that note, Tor is in Kathmandu now.
Wow.
He's learning Sanskrit so that he can read the original Natarajan trilemma.
Wow.
So in the 5th century, so I guess the first trilemma was outlined by this South Indian philosopher, and the only way you can understand it is to learn Sanskrit first.
Obviously.
Exactly.
Yeah, I do think I have a paper with the word trilemma in the title.
Did you solve it?
Well, that was a trilemma. We explained what the trilemma was. But yeah.
You should look up the absurdity of the Munchausen trilemma. It's hilarious. Yeah. Maybe you could use it to as a teaching tool.
Cool.
And Zafir is now ready to.
Zafir is in Switzerland right now, not learning anything useful, but he's going to start in September, and he might be studying more elephants. Yeah, he started his PhD.
More elephants.
Yeah, maybe. So he's interested. There is a good group in Oxford looking at it's a nice problem for us. It's a vibration of that elephant makes with the foot and how they sense it and how they behave accordingly. So the elephant transmits, as we discussed with Michel, relay waves by stumping, and they can sense that and integrate that information and adapt the behavior. And that's very long range communication. And there's a good group here doing this and see how it.
Wow, fantastic. So you could set up like seismometers and
That's
measure
what
the. Yeah.
So yeah. So this week he was in the workshop where they have new seismometer that record continuously, and they're gonna take them to test them to the zoo and put them in the ground and correlate that with the behavior of the elephants.
If they could only talk.
Yeah, well, they don't need to. They can stomp.
Oh, that's really cool.
Yeah, what I was discussing with an old biologist, a very eminent Jonathan Kingdon, that's written the Kingdon Guide to African Mammal, all drawn by every single African mammal drawn by him, because it's an artist. He's like the official guide. He's doing it was third edition. And he lives just outside Oxford. He's 90 years old and he only can see from one eye and he has Parkinson. He's trying desperately to finish that third edition, but he still has it completely. And he was explaining to me that interesting thing with elephant is that the elephant shaped humans, because by the time humans appear, elephant was a dominant species, and the environment in which humans evolve was the product of elephant shaping the environment. Like the roads they use that humans use were all made by elephant. All the vegetation and all that was also shaped by elephant eating. So we are a product of the elephant society before we wipe them out, essentially. I think that was an interesting view on the role of elephant in humanity.
Yeah, talk about extreme mechanics.
Yeah,
I'm more into moderate mechanics or minimal mechanics, but
soft mechanics.
Soft mechanics. So is this I guess theory of his, is that published? Like,
his first book in the 70s was The Evolution of Eastern African Mammal in 7 volumes. So it might be in there.
You should have Zafir. Zafir should read them, all 7.
Yeah. But he's also an amazing artist, and I think he's the biologist alive that has the most dissection and drawing of dissection from anybody. He discovered new species doing that, because he was in Uganda and Tanzania before Idi Amin Dada and all that, before he had to leave. He's African. And he had the right to any carcass of animals that would appear through any kind of deforestation or any kind of building. So they would call him and says, we have an animal, and he would go and dissect it and draw it. And he has this series of amazing drawing by hand, just beautiful black and white drawings of all these animals, hundreds and hundreds of them.
Yeah, it's an important skill that people don't. I mean, Ulrika took a course on drawing natural objects, right? I mean, it's you learn by doing that. You learn something,
Yeah,
right?
I'm completely amazed people are able to do that.
Yeah.
See something and put a paper representation of that. It blows my mind.
Yeah.
Of course, it's a lost art because, who can tie a book like I'll show? It's micrographia. It's all his hand drawing. He was an amazing person for drawing, amazing artist also.
Darcy Thompson.
Not
Did he?
Darcy Thompson. I'm not sure he was a. I don't think that in his book he had many drawing. He would just cut drawing from other people and put that in his book.
I see.
That's mostly.
Yeah.
I don't think that there is any drawing attributed to him. Francis Darwin was good. Darwin's son. A lot of the illustration in Darwin is from Darwin's son, Francis. A few from Charles, but there is really not that much illustration by Darwin himself.
Well, you know the story of him sitting in his garden and staring up at the trees. The housekeeper mused that poor Mr. Darwin, he's so lonely, he has nothing to do.
Okay, who do we have here? Matteo. Ciao, Matteo, again.
Now, this time virtually.
Yeah.
Okay, Matteo, you want to start?
Okay. So starting means introduce because the Ellen is the
Oh, I think you can talk about the EML webinar, then introduce Alan to introduce our speaker.
Okay, excellent. Thank you everyone for joining. Very excited to see you all here. I am the organizer of the new EML seminar webinar series. And today we're gonna jumpstart with an excellent speaker that is gonna be introduced by Alan, which is Alain Goriely. So we're gonna several webinars, sorry. And I'm gonna talk about the next webinar at the end of this talk. So I'm gonna welcome you all and quickly leave the room to Ellen for the introduction.
Yeah, thanks, Matthias. So the speaker today is Alain Goriely. Alain is my favorite scientific collaborator and friend, and I think you all know him. Let me briefly say a few words. So for those of you who don't know, Alain is a mathematician. He has broad interests in fundamental and applied mechanics and mathematics. He has pioneered the theory of biological growth and the mathematics of it. Many of you have read his amazing book on the mathematics and mechanics of biological growth. Alain received his PhD from Brussels and then moved to the US to the University of Arizona. And then in 2010, he joined the University of Oxford, where he currently is the director of the Oxford Center for Industrial and Applied Mathematics. Many of you know of Alain's amazing breadth and his models for plants and the umbilical cord, whip tracking and seashells, and most recently the brain. I think many have seen his amazing talks about that. He is currently also the Gresham Professor of Geometry at the Gresham College of London, where he gives public lectures to a broad public audience. And I'm assuming that has received broad feedback. Let me also share the three main things that I have learned from Alain personally, amongst the many things I've learned from Alain. So the first, if you know him, you probably know, the first thing you can learn from Alain very quickly is be curious. If you have a coffee with Alain, there's at least 5 things he encourages you to model. So he models everything he sees when he sits and has a coffee. The second thing is I'm more a computational person. So what I really truly learned from Alain is to always benchmark anything I do against simple possible analytical solutions. And I'm sure we'll see many of those in his talk today as well. And the third, and this is a very important life lesson, is that the only way to find out a good ice cream is to go to an ice cream store and try the pistachio flavor ice cream. So Alain and I have eaten many pistachio ice creams together. With these three things on our minds, I hope we have a great discussion during and after the talk today. So let's hear from Alain, and his topic today is about tilings and mosaics. So Alain, the floor is yours.
Okay, thank you. Let's see if I remember how to share things. Let's see. You tell me if it works. And so I do this. Continue to share. Okay. And then there is the bar at the top. I can't see my mouse, so I won't do it. I can't remember all the trick I learned from doing that during COVID, so I'll go straight in the talk and just use. Okay, so today I'll talk about a topic that actually started a couple of years ago when I was in Stanford during my sabbatical, working with Ellen on other fun stuff. And it's related to tiling, both of space and the plane. And it's a work that was really initiated by my good friend Gabor Domokos from the Budapest University of Technology. And he has done some other work. Akos Orvas is a mathematician also in Budapest. And Christina Regos was a PhD student working on such problem. And we have a couple of papers, one in PNS Nexus a couple of years ago, and the other one more recent in 2026 on the second part of the topic. And I'm very grateful for Gabor for inviting me to join and work on this problem. And we've done a lot of progress since then. It's been a very exciting topic. So it's a little bit different than your standard mechanical problem. We start with a problem in geometry, and I want to show you how it's connected to a mechanical problem. Okay, so one way to look at tiling in space is to divide them by either hard tiling, which are made of a polygonal structure like this one, or soft tiling, that's a metal foam, which are like this one. And it's really the difference, if you want, in the geometry of a plateau and the geometry of plateau. The Belgian physicists who study the shape of.
Sorry to interrupt, but I only see a blue screen. I don't know if it's
That's not good. Okay, thank you for interrupting. I don't even know. Okay, let's try again.
Okay, now I see. Now I see.
So what do you see now?
Now I see everything. I see some detail. Previously, I only see a blue screen.
Okay, so let me try again. So I see a lot of chats about please turn off. Okay, let's share my whole screen rather than the application window. Maybe that's going to be better. Or is that
perfect?
Oui,
Perfect.
c'est bon là.
Okay. So I was talking about these two different points of view. One which is very classical. It has thousands of years of study. The work of all the work of in the geometry is very classical, and the other one, which is slightly different, which is more work of typical in physics, where we look more at curved structure. And I want really to put the two together to develop first a mathematical theory of the same kind of filling in space, so things that can be tiled together, but for curved structure. So I will start with planar tilings. So if you look around you, you'll find plenty of examples of tiling in the plane. So tilings are a collection of cells that cover completely the plane or space with no overlap and no gaps. Right? So here are plenty of examples around nature or around architecture or art, like this one. This is a tiling for Alhambra from the 13th century. And what you see in this tiling is that the cells that are made of the tiling are both polygonal, like the little stars, or curved pieces that are repeated, in this case, periodically. It's one of the beautiful tiling that you can see in the Alhambra. That's a lot of diversity. So a few definitions. We distinguish monohedral tiling versus polyhedral tiling. A monohedral tiling in the plane would be the tiling by a single piece. So here is a little book, a wonderful book by Hokusai, the same Hokusai from the Great Wave. He was passionate about design, and he studied different ways of tiling the plane. And so here is one piece, that little piece that you see, the tile, that can tile by repetition the entire plane. You can have a monohedric tiling, which is also covered space with a single tile, but this one is not polygonal, right? It has curved space. And this is an example that was discovered 2 years ago. It's the spectrum. It's a non-periodic tiling of the plane with a single piece. And that was a big discovery after the work of Penrose. And here is Penrose on his Penrose tiling. So it is a picture I had to take when he won his Nobel Prize during COVID, and they needed picture to put on the poster. So this is Penrose on the Penrose tiling that's right in front of the Math Institute in Oxford, and it's made of these two pieces that fill, again, non-periodically the plane. You can have polyhedric tiling, and here is an example, one of the many examples from Escher, who played a lot with these and had a lot of study on this type of problem. And it covers, you have two different pieces that when you put them together, in this case periodically, also cover the plane. So that's the main difference. Now let's look at an example of polygonal tiling. It doesn't have to be the same piece, it could be random pieces. In this case, it's lava that's not completely formed, and you can idealize the lava by polygonal tiling in this case. And the element of the polygonal tiling are, of course, the cell, and the dual of the cell are the nodes that appears at the cell. They're the two main elements. So we distinguish convex cells versus non-convex cell. You have a convex cell is for any 2 points, you can draw a line between the two that's fully in the cell. And here is an example of non-convex cell. I make the difference because the mathematics, like in many cases, in mechanics, actually, the mechanics of convex objects is often much simpler, and you can obtain a lot of general result for convex cells rather than for non-convex. Okay, so for a cell, we can assign a property of a cell, and the first and simplest one is the number of nodes. So if you look around the perimeter of the cell, you can count how many nodes there are, place where you have 2 or more edges that meet. So in this case, we'll have 5 nodes for a given cell. But the one that I'm mostly interested is similar, but a little bit different, is the number of corners. And the number of corners per polygonal cell is really the number of full edge of the cell. And the difference is that there may be a node that are T-junction, so the nodes come in like that, like a T-junction, and you see that if you are inside the cell, you would not see this as a corner. The corners are just these pieces, right? So the corners that we are interested in is really a place where when you are around the edge, when you are on the perimeters, you have a discontinuity, and that's also important. So the corners are going to be the interesting qualifier for a given cell. Now, we've qualified cell by nodes and corner. We can also qualify a node. If you look now at one node rather than a cell, you can either count the number of cells that are around that node. In this case, there would be 5 cells, so the degree would be 5, or the number of corners. In the little circle, the blue circle that you have on your screen, the number of corners, there are only 4 corners, right? Because the last cell doesn't make a corners. And again, this is the one that I'm interested in. Okay, so let's see if we understood that. Here is a regular node. So you see that it has 3, in that circle you have 3 corners, but you have also 3 cells. and this is an irregular one. You have 3 cells around that node, but you only have 2 corners in that little circle, right? And if you look at this cell, it would have 5 sides, so that the number of corners is 5, but it has 6 nodes around its perimeter. Okay, sorry to spend some time on this definition. They're all a little bit obvious, but we must really get familiar with them. So now what I want to do is for, let's say, an arbitrary tiling, let's say a random tiling, with some technical hypothesis. What I can do is look at any given point, take a circle of radius r, and count the degree and the nodes in this circle. Then I take the limit for r going to infinity, and that gives me the 2 average number. I also keep track of the regular nodes versus the total number of nodes. So that gives me an idea of how many T-junctions I have in my tiling. In this case, for instance, I have 11 regular nodes out of 15. So I have 4 irregular nodes. And that's also an important property. So now for every tile, what I have is these 3 numbers. The average number of sides, the average number of degree, and the number that's the ratio of regular nodes versus total number of nodes. Okay, so let's try some simple one. The simplest monohedric tiling is the square lattice, where 4 sides, 4 edges meet at each node. So we have 4 and 4, the 2 numbers, and all nodes are regular. So my 3 numbers, 1, 4, and 4. And there are plenty of examples of regular square lattice around us in nature. For instance, from the book of Hooks on micrographia, he has the nice example of cork. And that was the first discussion about cork and property of cork. It was also the book that introduced the notion and the word cell and tissue in order to describe this structure, the cellular structure that all come from this. It was also the first scientific bestseller. It's an amazing book that's worth looking at if you have a chance to look at the original one. Now, hexagonal lattice, each cell has 6 edges, and at each node you have 3 cells meeting. And again, it's fully regular. That's one of the good friends. And there are plenty of examples in nature, for instance, the honeycomb. So the idea now is to organize that. We can go around and compute these numbers once they're well defined. And we want to organize that in the plane. We call that the symbolic plane. It's also called the Schläfli plane. Schläfli was a mathematician in the 19th century that worked on polytope and was the first to give this attribute to arbitrary tiling. His work was actually not well known at all, and it had to be rediscovered. But the first result that you can obtain about regular convex tiling is that the number of edges and the number of nodes are connected to each other. And they're connected as the inverse, as a hyperbola, and they only exist in this part of the plane. You have on one side the hexagonal one, the other side the triangular one, and in the middle you have the square one. And they're all that on a hyperbola. And you can create any example that you want like that. There are plenty of other ways, and they're all on that line, all convex regular tilings. Okay, there are also other one that sits on there that are maybe not as obvious to you. There's something called primitive tiling, and this might be the result, for instance, of shear fracture line that you might find in rocks. So if I look at these rocks, I'll see a bunch of line, and you can ask, what is the average properties of lines meeting in the planes? If I take random lines like that, then you realize that with probability 1, the intersection of 2 lines will dominate. There won't be any 3-line intersection. That's very low or 0 probability on average. And so the degree at each node is always 4. And if the degree at each node is 4, and all the nodes are regular because these are infinite lines, so you cannot have a T-junction, then you can automatically find that the average number of edges is also 4. So in a primitive tiling, you have 4 and 4, and they sit nicely here. You have other random tiling that you might know and that you might enjoy. There is the Voronoi tiling on one side, and then there is this dual on the other side, which is the Delaunay triangulation. Right? These are random based on some law, but they sit also at this place. They have the same properties. Okay, so these are the one that we are mostly familiar with, that we play a lot with, this in simulation and all that. But there are plenty of other ways to tile the plane. And for instance, you can have fully irregular tiling. Here is an example made of 2 shapes, the yellow square and the red square, and all the points are the same. So it's a transitive tiling. That means each node is really the same. If you look, you can just move it. And at each node is irregular because it's a T. And if you look in the little circle, you'll see that there are only 2 corners. So n star in this case is 2, and all nodes are irregular, so P equals 0. So in this case, all these fully irregular, completely irregular convex tiling sits also in the plane on a small hyperbola that's right there. And again, you can create many of these, and they have good reason of existing because when you build a wall made out of bricks, of course, you want that to be irregular tiling and not a regular one. Now that you've built these 2, it's easy to generalize that for an arbitrary P. P can be from 0 to 1. And in this case, all convex polygonal tiling sit in here. And so that's the full classification in the plane. It organizes them. And then Gabor went around with his students, and they started looking at a lot of different structure, both in leaf or in streams or in rocks and all that, and classify them. And they show that they sit at various places there. And so an interesting question is what's outside that? These are the simplest one, this convex polygonal tiling. What's this outside that region? Well, for one thing, you have hyperbolic tiling that live there. It's the definition of hyperbolic tiling here, where you have a negative curvature. You have a non-convex polygonal tiling that sit over here. Okay, and the question for us, and that was really the start of that whole work, was what sits below this? Is there a way to soften, to remove, to have tiling with less corners? So we know in mechanics a corner is not a good idea because it's a place for stress localization. And so the general question is, what is the geometry of objects of tiling that have fewer corners? And do they exist? And so that's my next part. And we can go back, for instance, to Okusai, and you'll find on another page of the same book this nice design. And when you look at this design, it's made of a certain number of pieces, maybe 10 different ones. And each of these, they tile the whole plane, and each of these pieces look like that, different shape, they rescale. And it's very easy to sit inside that shape and convince yourself it has 2 corners, right? Because there are only 2 corners. So here is an example with 2 corners that tile the plane. So it's an example of a soft polyhedric tiling that is a fewer corners. So back this time to a hook, micrographia, and that's a drawing of seaweed tissue. And if you remove the barbs, what you'll see, and you zoom here, what you'll see is that you have the same cell that repeats itself, right? And this cell, if you look at one corner, you realize that if you look at one node, you'll see that it has only one corner. So you really have each of these has only degree 1. So it has 2 corners, but degree 1. So that's already interesting. Here is a shape that is softer than the one that we deal with generally. And if you straighten the side, you can see that they make little pieces that you can just pile together. Another way to look at this is to start with a well-known tiling like the square lattice. You start with 4 corners and 4 edges, and now the idea is how do I change that to make it softer, to remove the corners. And the way you remove the corners, that you look at a corner and you're going to soften by making, well, you know it's not polygonal because we know all the polygonal. So I'm going to change one edge and change the half tangent so that it aligns now with the other half tangent coming from the other edge. And so what I do is I put a little piece of circle on the top and a little piece of circle at the bottom, and I've softened that shape. Now it has two corners and two edges. But you can ask now, a question is, can you go lower? But here is another example. If you go and buy an expensive bottle of wine, it might come in a little sleeve to preserve it. So what you do, you go home and you throw away the bottle of wine and you play with your little lattice. And what you realize is that lattice is made of also cells, unit cells that have two corners, and the degree of each corner is 2. So it's another example which has 2 corners. And you can repeat that. Now you go back in Schlafly plane, and where do they sit? Where they sit on this line. And now you can go one step further and prove that there is no way to do better, that the minimum number of corners in the plane is 2. And so we call soft cell of soft tiling any tiling that achieves this minimum number on average, or if in case of a single cell, it's the cell itself, of course. So as I say, you can start with any lattice that you know and transform it by, you keep the nodes at the same place. And what we want is transform a node remove the corner at a node, right? So we have all corners there. So we want to move the half tangent like that. And if we do it at one point, since it's periodic, we have to do it everywhere. And then we go to another place. We go here and smooth and align the half tangent again, and we obtain a shape like that. And we do that the same at every place, right? So there is a way to start with any given lattice and systematically make it smoother, softer. Okay, so now you can look at all monohedral tiling made with a single cell, and you can use the classification for the polygonal one and soften them. There are different ways of softening them depending on what you do with the corners, and you get these 12 different possible shapes that are soft tile, that tile the plane with a single cell that has only 2 corners. And if you look around you again, you'll see that a lot of them are familiar in shape. You find that in the shape of streams, in the shape of cells, bacteria, a blood cell take this kind of shape in epithelial, in tissues. You naturally have this shape occurring, or in the work of architecture, like the work of Zaha Hadid. She has a lot of this shape that in a way very intuitively she created shape with fewer corners. Here is an example that Adrien actually gave me, also from Escher, where you can see that these 2 fishes make a unit cell that is one of the subcells. So a question that you had, okay, you can see them around, but a question that I had is how generic they are. And when you work in tissue mechanics, like maybe a lot of you do, you learn that in order to do simulation with tissue mechanics, you use vertex model, where you essentially rearrange cells that are polygonal in shape with various rules depending on the energy. But I don't think this is generic. And if you look at, let's say, if I start with random number of disks and I let them grow inside a disk until they cannot grow any further, what I obtain is generically a shape like that. Of course, each of the circle has no corners because they're circle. But if I think about the white space also as cells, I can count the number of corners I have, right? These are all places where I have corners. And if I count the cells, the corners in each of these white cells, and I add them up, I have 10 disks plus 12 voids plus the outside, that's 23 cells. And I have a total of 42 corners. And so my average number of corners is less than 2, which is due to the fact that I'm not in the whole plane, and the other characteristic of the disk is lower. So the bond that I gave was for the whole plane. So this is an example of soft tiling for that geometry. But of course, you're going to tell me, yes, but things are not rigid, cells are not rigid. That's true. So if you now let two cells grow that are not rigid, they touch each other and they start deforming. And as soon as you have any amount of bending, so not a foam, but real cells that have a certain bending stiffness along the side, on the exterior, then they always meet tangentially. And so they do not create any more corners. So even if I have my bunch of my disc and grow and deform them, when they're going to push against each other, they're not going to create corners. So soft tiling, actually the generic form of tiling for soft material, unless something else happens. And that's also very interesting because now the idea is that during morphogenesis, you start with soft tiling, the cells grow and they push against each other, they start making an epithelial sheet. And if you count, these are actually soft with respect to my definition, if you take the extracellular space also as a cell. But then there is a transition, and that's an idea that dates back in morphogenesis by Honda in the 80s and 90s, where it rigidified, become hard, right? And in order to do that, whether you are in plants or in mammals, you need extra physics, you need extra mechanics in order to bring the three corners together and make these, you go from soft edges to rigid one, to make a polygon. And these are the tricellular junction. And so in order to achieve that, you need that extra mechanism, biological mechanism, to go from soft to hard. And you can ask, why would a tissue needs to be hard? And that's also interesting because Honda already put the hypothesis forward, is that during morphogenesis, there is essentially a phase transition where the tissue can be seen as liquid, where the cell can rearrange themselves, to a tissue that is rigid. And you need this tricellular junction in order to rigidify that tissue. So now the tissue is both rigid from a mechanical meaning and rigid in the same way that's not soft, as I told you. And I thought that the problem was very interesting and something good to study. And I thought, that's a good project. But then this week, I found out that the latest edition of Nature Physics, and a nice cover, so that's just June 2nd, I think. It's just appeared. And a beautiful paper by the group of Nicoletta Petridou in Heidelberg, where they look at the reorganization of tissue. And they do beautiful experiment and some interesting good math also, where they show that this transition occurs and that this transition is driven by adhesion. And thanks to this adhesion and tricellular junction, you have a rigidification of the tissue. So that connection is it's already made and very interesting. So that was for 2-dimension. So what about hard space tiling? Where that gets very hard. There is plenty of space in space. You can do all this tiling with this multiple polyhedra, for instance. But let me go back to Plato. And Plato thought that there are, of course, a Platonic solid, there are 5 solids, but the important part for him is that they would tile different elements. The cube would be earth, the tetrahedron would be fire, the icosahedron would be water, the dodecahedron the universe, and the octahedron the air. So he thought, or depending how you read the text, that these 4 polyhedra would tile space. However, Aristotle already knew that none of these actually tile space, and he thought that the cube and the tetrahedron would tile the entire space. And this was known until about the 15th century, where people look again. So if you look, for instance, at the cube, the degree of a cube is 8, because at one node of the cube, one corner, you place 8 different cubes, right? This cube is about the only one that I can do and most people can do in order to realize in 3D space. But what about the tetrahedron? So the tetrahedron is more complicated, and if you try to guess how many tetrahedra come around the same point, so if you start packing the faces together, It's not that the exercise is not easy to visualize, but if you do the computation of the partition of the dihedral angle, you realize that there is no way to pile tetrahedra with the regular platonic tetrahedra in space, because you can put 5 around the corners, but not 6. You would need about close to 24 to pile it together in 3D. But as soon as you put 5, you have no more room for the 6th one. So this is not an example. Only the cube is the only platonic solid that tile space. But of course, there are plenty of other ways to tile space. For instance, you can do Archimedean tiling. You start with the regular octahedron, it's beautiful, and then you truncate the side, and now you have hexagon and squares. And this one is a tiling of space, and was heavily studied by both Fedorov and Kelvin, and we'll get back to these. There are other shapes that are tiled the entire space, and Fedorov showed that there are only 5 possible ones that tile space by translation in 3 possible directions. And these are the 5 classes of polyhedra. So now the question for us is, can we soften these? Can we bend the edge in some way as to reduce the number of corners? And that's the idea of soft cells. So remember, soft cells at 4 corners and 4 edges, and we went to 2 corners and 2 edges. And now the question for you to think about, and it'd be good to have a little, I think you can do a little poll in Zoom, but let's not go into that. It'd be good to know, because it's a good exercise trying to figure it out. If I start changing the shape of the edge and the shape of the faces, how can I reduce the number of corners? What is the minimum number of corners that I can create by this process, by this softening process? I start with 8 corners, 12 edge and 6 face, and how low can I go, really? So now that you have a minute to think about it, I'm going to give you the result. So the result, the theorem, is that in 3D you can go to 0 corners. And it's a little bit surprising, but it turns out that there is a lot of space in space to move things around. And the proof is beautiful, because all you have to show is an example of that. And the proof has 2 parts and no computation involved. The first one is for me to show you the shape. This shape has 0 corners. This is this one. Do I have a bigger one? Yes, right here. So this shape, if you follow the edge, you realize that there is only 1 edge, and there are 2 faces, first 2 soft faces. And that's the first part of the proof. And the second part of the proof is that I take 2 of these, and the shape of the round shape here is the same on both sides, so I can put them together like that. And once I have that, I have a prism that has a square section, and I know that the square tiles the plane in the other dimension. And that completes the proof. So you can find soft cell into. But of course, you want to do it systematically. And the idea, again, is to introduce a systematic way, a procedure to start with a given lattice for which I know the node, and bend the half tangent so that they align. And so I take a node, they're all the same, it's transitive. And so I follow the half tangent, I bend them, I bend the one below. But of course, I have to do that at every single node again. So I repeat that operation at every single node. And then I extract the one cell that I obtain in the process. And I have a lot of freedom now to choose what my edges and what my faces are. So the one that we choose are Dubin's path, the same Dubin's path that we find in control theory. So given 2 tangent, the Dubin's path is the shortest path with the lowest curvature, so with a curvature bound. And the faces themselves are minimal surfaces that we choose. You can choose anything you want, but it seems like a natural choice. And you'll see the connection with minimal surface in a moment. So can you do that always? The problem is now that if you have a given tiling, what you do at one node has to be done at another node, and they have to be compatible. So a couple of years ago, we obtained a nice theorem, and I'm not gonna read the theorem, but I'll explain you that you can do it if a certain condition is met. And I'm going to show you the condition on the cubic lattice. So if I take the cubic lattice, all the nodes are the same, so I can only look at one node. I take a little sphere on that node, I look at the intersection of the edges with that sphere, and I create a polyhedron based on that. It's called a vertex polyhedron. In the case of a cube, it has eight nodes, so it's a octahedron. Once I have an octahedron, I take the dual of the octahedron by swapping edges and faces, and I obtain the cube. And when I obtain the cube, I can look at a Hamiltonian circuit on the cube. An Hamiltonian circuit is a circuit that goes to every edge, that goes to every node without coming back on itself. And in that case, we show that you can always, starting with a given lattice, if you can make this construction and find the Hamiltonian circuit, you can always find a softened version of your lattice. You can always soften the lattice. And we had a conjecture at the time that that condition is actually not necessary. It turns out that I received a paper about a month ago from people also in Hungary, and the claim of the paper that's now being reviewed is that indeed that conjecture is correct. They generalize it a little bit, but that every polyhedral convex tiling can be completely softened. You can always do this operation. They didn't use a condition because a condition is actually very hard to prove in general for an arbitrary polyhedron. So they have a different techniques there. Okay, so that's good news. You can always start with that and soften it. So here is an example. Started with the octahedron, and you have the cell, and you can now soften it systematically. And when you soften, you obtain this shape that I showed you on the first slide. And this shape is a soft cell that fully tiles space. And you really, just to convince myself, I had to 3D print them. And when you 3D print them, you realize that the faces are compatible and that you can start putting multiple ones together and tile the other space just to convince yourself. Right, so this is the wireframe of it, and then you can start piling them around. It's very nice. It's one of my favorite, this one. But it turns out that since we have the edge bending algorithm, you can start with the parallelohedra of Fedorov or the tetrahedra. There are plenty of tetrahedra that tile space also, not the regular one, and you can soften them. And it's not always obvious what the shape is. Here is, if you can see the tetrahedra is very bizarre. It has this very nice intrinsic shape. And to convince you that it tiles space, okay, I have to find which one is the tiling. When I put two together, again, I obtain a prism. So if I put them all together, I obtain a prism. And the prism has a triangular section that tiles the perpendicular plane. And all of these are soft version of the polyhedral tilings. And again, if you look in architecture, ideas not often implemented, you find good example of that. I want to show another example, which was very exciting, actually. And the example is found in nature, and it's in the Nautilus. So typically, we found that, Derek and I found that about 20 to 30 cover of math textbook have a Nautilus on the front page, and none of them talk about the Nautilus or to say something wrong, like it's a Fibonacci spiral. It's not a Fibonacci spiral. So we all know that shape. It's iconic. It's sort of often associated with mathematics and beauty and nature and blah, blah, blah. But what we do not know is the chambers. So what is the shape of the chambers? We see them as a 2D, right? So when they cut Nautilus, they cut 1/3 and 2/3. This one is the 1/3, is the cheapest part. So that's why I have it. And what you see are these little shape, this moon-like, this crescent shape, very much like Hokusai. So they look like the tile in 2D, but they're really 3D shapes. Now, what's interesting with the Nautilus Nautilus is a chambered mollusk. It's a cephalopod. And the Nautilus behavior is very simple. It's during the day, it's deep in the ocean, maybe 100 to 700 meters. So very, very high pressure. It comes back up to about 100 meters or so during the night to feed and then goes down. So it goes up and down, and it does so by changing the concentration of different gas in different chamber by a muscle, a siphuncle that goes around the different chamber. So this is why it's chamber in the first place, was these chambers exist in order to control buoyancy. But the interesting part is the 3D internal shape, and this is a CT scan of the 3D, the internal shape. And if you extract this shape, this chamber shape, it looks like this. And now you can pull one chamber and look at what it looks like. And again, if you straighten it a little bit, it looks like that. And this is a soft cell. It has no corner, which is very good news for the Nautilus, because 700 meters is a lot of pressure, 70 atmosphere, as you know. And it has to, no, it's a 700 atmosphere, and it has to resist that pressure. So no human can go down more than 30, 40 meters before having problem with pressure. And the lack of corner is particularly useful in this case because, again, you won't have a stress localization under pressure. Of course, there is a lot to think about. It might be a simplistic explanation, but it's certainly a starting point of understanding the role of soft cell in nature. So here is a way to stack them. You can fill space now with this logarithmic spiral by making bigger and bigger, or you can make a more Euclidean version of that by having a single shape like the one on the right and pile them up, again, like prism. So now we're quite happy with that result, but by the end of the first paper, we realized that there were other shapes in nature that are not covered by the explanation or the construction that I had before, that related to triply periodic minimal surfaces. And triply periodic minimal surface are absolutely beautiful mathematical object of geometry, but they also have seen a lot of application in microstructure and mechanics, both for their property for heat conduction, for water exchange, for mechanical loading, and so on, and even for optical properties. So let me start with the truncated octahedron. And I'm going to show you what is the relationship with certain type of triply periodic minimal surface. So triply periodic minimal surface, as the name suggests, minimal surface that can be obtained from a unit cell that's repeated periodically in the three directions. And it divides space in two different regions, inside and outside, if you want, completely. So they're quite difficult to picture, except the simplest one. And you'll see that in a second. So how did we build the soft truncated octahedron? We took the nodes, and we don't move the nodes. What we move is the half tangent at the nodes. And if you have the half tangent in red there for the polyhedral version, you just move it a little bit and obtain another half tangent that soften it. And all the nodes are equivalent, so that you only have to do it at one of them. Okay, so the question is, what else can I obtain if I change this half tangent in different ways? Well, here is the cage of it, just where the nodes. And if I change it, if I move the half tangent in the other direction, what I obtain, if I choose it carefully, is this object. And this object is very nice because it's the unit self of the Schwarz-P surface. That's the easy one. The Schwarz-P surface is obtained by repeating this unit cell that you see here. But even this Schwarz surface is not that easy to see. And it's also soft cell in the same sense. That means if I have this unit cell, I can put other unit cells around it to fully fill space. Right? It has these properties. It has these double Labrien properties that you can start piling them. Here, somebody has made them out of concrete block. And you can, if you fill them, you'll see that these are unit cell for the soft cell that tie the entire space, right? And then even these one that are so Euclidean are not easy to picture, because if you look at the labyrinth, the double labyrinth, if you enter the first floor, you realize you can only go to the third floor. So it really divides space into these two different half space. The simplest way to do a half space is to cut the space in two. And here is a much more intricate way of halving the space in with a surface that repeats itself and goes around space. These are what the triply minimal periodic surface is. So you see that I left a space there because there is something else interesting that caught our attention. There is another structure you can create there by also changing the half tangent. And what is there? Well, to understand that, you have to go back to Plateau. And the rule of Plateau is that in order to have a balance for a foam in the plane, you must have 120 degrees in order for surface tension to balance. But in space, since you have four junctions, you need 109 degrees. So you have four. And Kelvin had that idea that in order to have a good model for a foam, he says, why don't I start with the truncated octahedron and slightly change the half tangent and the face, now the face is curved, in order to create that condition of 109 degrees. And that's the Kelvin cells. There's no exact analytic form of it, but that was the construction. And what's remarkable with the Kelvin cells is that to this day is the example or the conjecture is that it has the smallest surface area to volume ratio of a single unit cell. And so here you have now part of the same family, truncated octahedron, soft version, the Kelvin self, and the Schwarz-P surface all connected. It's quite remarkable from geometry that these are actually simply connected like that. Now, once you have one, you can build other one. The most amazing one is the gyroid. The gyroid was only found in the 70s by Schoon in a very nice NASA technical report. And the unit cells, again, are soft cells of this type. And you can see right away that the gyroid of Schwarz-P surface, it's very hard to wrap your head around these as surfaces, the inside and the outside. So the blue and the yellow correspond to different space. So if I have oil in the yellow part and vinegar in the blue part, you wouldn't be able to make vinaigrette, right? Except that it's becoming interesting now. If this surface is a little porous, you can optimize the exchange between these two. That's why you have such nice properties that are used for thermal exchange, among other things. So now in terms of geometry, you can organize these depending on the different half tangent, and you have a new connection between this triply periodic minimal surface by this construction that was not known. There are different ways, different families, but this is a new way to connect them not only to other triply periodic minimal surface, but also to other structure like the Kelvin cells or the soft version and so on. And that was the content of the second part. What's interesting is that there also a nice model as atom or mesoatoms, as they sometimes call, for diblock copolymers. So diblock copolymers are structures that are made of two different polymers that typically would separate, but they're also covalently bonded. So they both want to be as much apart as they can and together by the covalent bonding, and that was created a condition for a minimal surface between the two. And under the right condition, you can create this structure, and you see that the different unit cells of the triply periodic minimal surface are like little Lego bricks for this structure, right? So soft cells place these Lego bricks from which you can assemble more complicated structure like the diblock copolymers. So our last application, which is a little bit more on the fun side. So Gabor made this nice wire frame of the soft octahedron and then dipped it in soap. And as soon as you dipped it in soap, the soap film adopt the minimal surface, so you naturally create a surface that is a soft cell. But then he thought, well, okay, we thought maybe we can do better. Is there another way to have a full soft cell that can be created by water? And the process is, yes, he managed to convince the Hungarian Space Agency to send a wireframe of it in space. And all you have to do, as they say, all you need to do is add water, right? Because if you add water, if you don't have a frame, it would be a ball, minimizing surface tension. And if you have a frame, it's going to adhere to the side of the frame and also minimize surface tension.
International Space Station. Tibor Kapoor cautiously adds water into the skeleton.
And it's a little TikTok video that we made in the department to showcase that, based on the video that the space agency made in the space station.
This is the first instance that a 3D shape with negative surface curvature has been realized from liquid water.
So I'm not sure what it's really for. I mean, it's obviously for education, but one thing we did is make an astronaut happy, or really happy. So I think that was an achievement. So I think I'm running out of time. So let me conclude, a brief conclusion, and we can have a discussion. I think we have a good understanding of the basic full cell classification and partial one of the 3D. There's so much possibility in 3D that there are we suspect many more interesting families that's going to pop up. And for instance, the triply periodic minimal surface. There is an interesting construction related to Schwarzschild with particular conduction, with carbon tubes and so on. The Dieburg copolymer, I briefly say that the gyroid structure have also this nice optical property because of the periodicity. They have optical gap, and that translates into nice models. For instance, for beetles and weevil, in this case, the carapace has this optical property that they are in the light that are inherited from these. And with that, I have to say that it was also voted the coolest mathematical discovery by Scientific American. So that's one also for the list. And I thank you very much.
Yeah, thank you, Alain. That was amazing and nothing short of any of your other talks. I really like the 3D printed demo. I think everybody here has, when we saw it, would wish to be in your office and play with all your 3D
Yeah, it's too bad. Usually I travel with them so that people can play with it. You really
exactly. I was hoping I could touch it.
To be able to enjoy it.
Yeah, no, that's very cool. Maybe I start with the first quick lead-in question, and then we can ask to open up to the audience. So nature seems to prefer smooth cells, and you've shown a lot of examples at the beginning. Do you think we can learn something from that? Or maybe on a higher scale, when we do our models, we usually use these sharp polyhedral structures. Do you think we need to use softer cells in models too, like finite element models or mathematical models? Does it tell us anything between the physics that's more rigid and the biology that's more soft?
Yeah. I mean, there is a good reason why we use straight edges and faces, because of course it's easier. It's linear mathematics, so everything linear is more convenient for us. And that's how geometry was built. But if you look around in nature, even if you look at the honeycomb and you look close enough, you realize that the cells are not straight line and all that. You really have to put a lot of energy or specific mechanism in order to sharpen and make edges like that. And of course, there are plenty of reasons why you don't want that, or it's hard to get. As we said, stress localization. I think that nature bores corner, yes, and naturally the shape evolve. When you put them together without any extra mechanism, the shape will be soft shapes. Then there are other processes for which you need teeth to be sharpened, like in the tissue rigidity. And then you have, through evolution or whatever process, you really have to sharpen to sharpen teeth and rigidify and find new mechanisms in order to be able to do that. So I think the generic shape is soft, and extra physics must add that. Now, whether or not we can translate that and let's say at least better basis for finite elements, I don't know. At least way better way to do things, because following nature, maybe we also want to do that. We all have problem at edges and concentration and phases. This is where a lot of problem, both mechanics and computation, come in. So maybe we can learn, but at least it's a balance between simplicity and being more truthful to what is, or being advantageous to that.
Well, definitely very inspiring. John has the first question from the audience. Please go ahead.
I can't seem to turn my camera on because the host has disabled my camera, but here it is. I hate to be anonymous. So, I mean, mostly you discussed, or it's implicit that you're talking about equilibria. And like if I think about the Shefley diagram you showed, how would external forces move me around in that space is a natural question for me. So that's one general question. You showed examples of shapes like a riverbed versus a plant. And so in the vein of the first question, one natural question is, what's the difference in this framework between a non-equilibrium steady state and an equilibria, and how do you reach that? Which goes back to the very first examples that you were giving about convex versus non-convex shapes. And so then to Ellen's question, a lot of nature doesn't mind corners. For example, crystals. So if I think about the equilibrium shape of a crystal, that's given by the Wolf construction. So there's an invariant which requires the surface free energy, not the surface tension, plus its second derivative with respect to the normal. And then there's an analogy called the Frank-Chernoff construction in crystal growth, which is an exact analogy for normal growth of a crystal. But the problem there, which is back to the first question, is that it ignores initial data that are not convex. So beginning with a non-convex shape, getting a convex shape, anisotropy, those are the kinds of questions that came up when I'm looking at these shapes, like where do they come from in nature? They're there, but how did they arise in the first place?
Yeah, they're all very good questions, and I'm not sure I can answer them. Maybe with the collective wisdom of all the panelists, we can try to answer them. So please join in the conversation. There is the first one. I think there is something very interesting about the dynamics of a process and how it evolves in the symbolic plane, or it changes. That's for sure. I think there is something very interesting in terms of the dynamics that's completely unexplored, I would say, as far as I know. And whether or not you have a natural tendency to go up or to go down, or create a structure depending on a different transition that you have. Some of it can be answered probably if you look at the elementary transition that you have. But that's still fully remain to do. Thinking about your other question about crystal, and that's very good. Of course, atoms and crystal have this very rigid organization for good reason. And there's been for centuries now, basic question is how do we distinguish something that's biological versus something that's physical or chemical purely? And it's a both philosophical debate, but it's also a scientific one. And maybe there is an interesting transition there between the geometry of this object, that intrinsically the biological ones are on the soft side, and then the non-biological one are on the rigid side, that they satisfy different constraint. And maybe at the cellular level, that's due to the fact that you have to establish a wall, both in plant and animal, a wall in order to have an identity of a cell, right? You don't have an identity of a crystal element, but you have an identity of a cell. And in order to do that, you must endow the wall of certain property. And as soon as you endow a property, one of them is bending stiffness that you cannot really neglect. And if you do that, then you get this tangent contact. And that's a soft contact by default. Now, the other example is the Young-Dupré condition for forms. And that automatically gives you an angle, right? Because there you can neglect the bending. There is no bending energy associated with the edge of a forms cell. And that might be in the column of non-living things versus living things. The interesting things, of course, is during morphogenesis, you would start in the soft side and then transition to more rigid, which would push you in the non-living part or the more subtle
Yeah, I
part.
mean, you show this Honda 1983, this transition where you become more polygonal and stiffer.
Yeah.
And therefore you would expect there's a transition where that the second derivative of the surface energy with respect to orientation becomes important and it's hard to say bend out of the plane.
Yeah.
But
So
you
it's
don't.
really a rigidification. It's more than that. You also create plaquette like that. So if you have 4 cells, if 3 cells, and you look at the intersection, or 4 cells coming together, or 3 cells, so you have triple. What you want is a bar in between. So you really want to bring that triple cellular junction together, and that's that prevents that diamond to change shape. So you have a really topological rigidification. If I take 4 bars together, it's very hard to make them rigid. They can pivot. But if I put a bar in between, that's already makes it much harder. You have there is a general theorem for rigidification of networks like that. But on top of that, you have extra condition like you do. So bringing these corners together actually does that. It creates this network of force that prevents shearing. And we know that shearing is always bad in structure.
But in biology, you don't see facets, right? I mean, in crystals, you see facets.
Yeah.
Right. So there's a homogenization scale somehow where the stiffness is on the large scale is not important, or the bending stiffness doesn't seem to be important on some scale, or there's an external force
Yeah. So
involved.
yeah, there is a natural scale for bending, right? That you can find.
Yeah.
It's always there, but you can scale it down, and you have a singular limit where you go from a parabolic contact to a straight contact.
Yeah.
Great discussion. Maybe we can move to Davide. There's a couple of people also who have raised their hand. Davide, maybe you want to ask your question?
Thank you. I mean, great talk. This is the second time I'm hearing this talk this week. And actually, this is the extended version. And compliments is really enjoying. I enjoyed more the second time than the first. So my question would like to turn a little bit the attention on mechanics of solids. And I think maybe you have already imagined what could happen if we start from packaging of spheres which do not fit because they touch at points, and then we subject them to an increasing compression or isotropic or not. How do they transform in dodecahedrons or whatever?
Yes. 3D is always very hard, so I don't know. I'm at the level of trying to figure out in 2D just for this growing disk and now making them more general and making them soft. I don't know what are the shape. There are a good example for that in nature, for like 3D shape of growing things. A good example is potato. If you look at the cellular structure of potato, they're like big cells that are against each other, like balloons that push. The fat structure, when it's not surrounded by tissue, has also this type of properties. So I don't know. This is exactly the direction I want to go. We have a nice application with lily pad. When flowers grow on a pond and start pushing each other, then they get also a little bit polygonized and start squeezing. So if I understand that, that would be a much nicer first example to understand that. And it's one of the projects that we have ongoing with people at the Botanical Garden here.
I think that if you open a pomegranate, you will see that the seeds are arranged, are squeezed in a way that they look more or less like
yeah,
your.
that's true. That's true. They have this shape.
Great.
Thank you.
Next is Michael.
Yeah, hi, Alain, and I joined Davide also to congratulate you on an even better talk or more extended talk than 3 days ago. My first question was about, I think you've touched upon it. Would there be any application for finite elements, creating finite elements that are soft?
Well, I would redirect the question to the many experts in finite element that are in the room and tell me if they think that would be something that would be advantageous. Because to be fully honest, my knowledge of computational mechanics is usually to ask Ellen to explain to me and do it for me. So I do not know exactly what are if you want, make a list of the requirement of what you want in a good finite element basis. Would soften it, make it a better basis with respect to this requirement? So what do you think, Ellen?
Maybe we can open this up and people can think about
anybody,
it.
Please feel free to
so
comment.
I suggest we go to Hadrian for now, and then the finite element people can think for 2 minutes, and then they can give us some more open discussion with everyone. So let's postpone this for one more question, and let's take question from Hadrian.
But I had one question about the ISS experiment. That is fantastic. I don't know how you managed to get that approved. That's the dream, really. But I was wondering what would happen if you had a cubic wire skeleton and filled it with water. What would the water do?
Well, if you do it well, the minimal surface of the water would be flat.
Right.
Whether or not you can actually do it, I think you could. I don't see any reason why it should be different if you take a square face. No, not the soft cube, the actual cube. If you take the wireframe of a cube, I think it should be flat.
It will fill up the faces of the cube.
Yeah, so it would fill the interior, adhere to the edges, and as you keep filling, it would be straight. Actually, for the octahedron, there is a flat part here, and you have a little piece that's also flat.
So it's possible to have flat faces.
Yeah,
okay.
Yeah.
Thanks very much.
I don't know if they've done the experiment. As you can guess, it's very expensive to do experiment in space just to humor a few mathematicians.
I can only guess.
But they also always have to do experiment, right? Because they have these tools, they send people, they have an outreach budget and all that they have to show. So if you can convince them to do something fun, they like it.
Great, thank you. Who else wants to ask questions to Alain or comment on the finite element or visualization?
I had a question.
Yes, please.
I was raising my hand. I lowered it. I thought you saw me. Thanks, Alain. Great talk. It's the second time for me, but it's always a pleasure. I have a general question. So all the soft tiles you showed were derived from hard tiles or even prismatic tiles. Can we envisage a world of soft cells that exist in their own right without deriving from hard cells?
Well, so yeah, it's a very good question. Of course, we started with given one that we know filled space and then soften them. or so that unit cells from triply periodic minimal surface have satisfy all the conditions to be soft cell as such. And the question is whether or not there would be a soft cell that has no hard cell equivalent for which you couldn't rigidify. I think probably not. We might try to make a theorem out of that. If you assume the existence of a soft tiling, I think you probably, because of the combinatorial condition, you might always be able to rigidify, but I wouldn't be sure. It's a good question. I really don't know if it's.
There are tiling of space that do not have straight faces, though. Maybe that would be a
So
starting
even in space, in the plane, the spectra, you cannot rigidify it. You cannot make it polygonal, for instance.
Yeah.
Right? And keep the same combinatorial structure. So that's an example of, but it's not a soft one. I don't think we can prove that it cannot be softened because they are incompatible conditions. But if you start with a soft one, can you always make it rigid? My guess in space, it would probably be possible to find a counterexample of that, but I don't know. It's good problem. It's good. I'm gonna go home with a bunch of new problems. So nice suggestions.
Jimmy had a question.
I have a question. Thank you, Alan. Fascinating talk, Alain. This is my first time to hear this talk, but it's really interesting. So when you have the soft cell 3D, the condition is it has to be space filling, and you have curved surfaces and edges. What determines the? I'm assuming that if you 3D print the edges, for example, you showed the NASA showed one of these examples. If you put water in it, self-contained, and the shape of that, I'm assuming, is to minimize its surface energy. But assuming that the edges have a different energy from the surfaces, then the question is, how does it balance these edge energy versus surface energy?
Yeah, no, that's a good question. So the choice that we made is a purely geometric one. It's one of natural, I would say, that one of the simplest one that you can get. But there is no restriction on the shape of the edge or the shape of the face, as long as the shape of the face has the right boundary and it has the right symmetry group with respect to fitting with another one. So the minimal surface is the one that would be preferred if the edge didn't have themselves surface tension. But in principle, you could ask the question, what would be the minimizer of that? Well, once you have the edges, the face have to be minimal surface. So the question is really, what is the shape of the edge that minimizes the overall surface tension?
Energy, right? Yeah. So I'm assuming that, or imagine that eventually, let's assume that you have a cellular structure of some sort. If it turns out that cellular structure, the cell walls would always have higher energy than the interior, and the edges would always have certain amount of energy associated with that. If the overall 3D construction is not the energy is not minimized, over time it would evolve. If it's a plant, it would move its shape eventually to minimize its energy. What is that shape?
I don't know. It's a good question. An important consideration, of course, is not only the surface energy, but the adhesion energy that's related. Right.
Indeed.
So you could have different, like you have in the cell, you might have different energy at the node versus energy at the edge versus adhesion energy at the on the surface. And then you could evolve to different shape. So we haven't put mechanics of like surface evolution based on that. We've assigned the phase, but that's a good question.
Yeah.
I think you could use Ken Brock as surface evolver, maybe.
Yeah, absolutely.
Indeed.
There is a general surface evolver that works well for that.
Yeah.
It would be fun. So you probably would start with a regular hard lattice. You would soften it to create it, and hopefully by just changing the edge, the surface of each part would naturally evolve to one of these shapes. That would be a nice construction to try.
You mentioned Kelvin, but you didn't mention Weir and Phelan.
Yeah. So Weir and Phelan came and managed to beat the Kelvin estimate by finding two polyhedra that also tie the full space and has a lower energy to volume ratio that beat the Kelvin cell by 2 or 3%, I think. And that was a huge discovery, of course, because that was the first time that somebody had found an example of a better way to do form. And it's interesting because the Kelvin estimate or Kelvin conjecture is still there because it's a single cell. But what they show is that a configuration that breaks that condition of a single element actually lower the overall energy. And so a natural question is, well, I could get multiple polyhedra now. Is there one that beats that further beats that? And that's, as far as I know, is still an open question in these fields. There's a lot of nice open problem like that.
Yeah, not to make the problem even more complicated. You have, in this case, you have regular volumes of these shapes. Imagine if you have random distributed volumes, what would be the shape evolution eventually that gave rise to the preferred?
I think that touches John's question about you really have to do it from a statistical perspective, evolution of the distribution of shapes, and try to understand how that goes.
Indeed.
I think it'd be interesting to look even in the plane, starting with a regular polygonal lattice and let it evolve by softening it, letting this space open. Because most of the construction for tissue and all that always assume that these points exist, but you can remove them. You can remove this junction and let them evolve, let them round the shapes in a way, but still having adhesion so that it's still favored to have contact. And yeah, that's open. But there is, John, there is a whole literature on this type of distribution in statistical physics with shape. I've looked a little bit at that, and it's mostly with hard shape, but there is a little bit with softer shape also on that.
Yeah, I mean, dates to Avrami kinetics sort of looked like one of the examples you gave.
Yeah.
And I guess a year before we were failing, I was visiting Dublin and Alan Newell was there. I gave a talk and we were forced to go to the pub. Long story short is that these two guys at the bar were arguing whether Beamish or Guinness was better. So we sketched out a proposal, and Dennis sent it to both Guinness and Beamish, and Guinness funded his PhD students for about a decade on beer.
On foam?
Yeah, foam, because Guinness likes to have their foam in so there's surfactants that are transported along the surface. That changes the surface tension. So the evolution of the bubbles, once they get in the foam, they wanted it to be as slow as possible. Yeah.
Here is a perfect example.
Okay, what other comments do we have? Mattia posted on the finite element or space filling tessellations. Mattia, you want to comment on?
Mattia has an idea. Good.
Sorry?
You have an idea?
Actually, I think my comment about tessellation is inappropriate because premise I'm not an expert on computation. We use computation, but we're not really super advanced. One of my students a while ago was talking about mesh-free methods and was talking about isolation that was Voronoi. But the mesh-free method, to my understanding, are focused on a nodal description, but then they have like these decaying kernel functions, right? So in a way, they're less accurate than finite elements, and they are basically there is this decay. So the edges there are probably not as important as in finite element, because in finite element you use these nodes that are at the edge of your RVE, so to say. And there we do have on large deformation, we keep encountering, especially when doing indentation and punch and cutting, we do have problem of element distortion. And therefore, in large deformation especially, because your element changes its shape from this initial one, certain edges configuration could actually become critical and it can create some problem of numerical instability. So certainly there is an avenue there for exploring.
Great point.
Yeah.
I recall that there was like when people were going from 2D to 3D, there was huge discussions in finite elements and people landed on just tessellations or triangulations because that was the easiest to fill space, but then also just to fill space with other shapes that are not tetrahedral. It's really been in finite elements challenging.
Yeah.
Okay, who else would like to engage with a question or comment or has new ideas for Alain to work on in the next 10 years?
Yeah, I'm really short of a problem in a research project right now, so I welcome a refill, as I say.
I think anyone who has had a coffee with you would know that you would find all kinds of problems around you. So you've inspired, I guess, many of us to look more closely at nature and to model it. Do we have any
Exactly.
more?
I mean, it's very typical of this problem because once you have this in mind, you go around and say, this is a soft cell. Why didn't I see it before, right? You're going to go around and see tessellation and says, yeah, we think about this as polygonal, but look, they're round and these have these nice properties.
Even the beginning where you showed the river and the landscapes, I mean, it's really
if you
fascinating.
start thinking them as different zones, you'll see that they occur very naturally.
All right, who else would like to comment? I'm sure many people will watch this because it's been very inspiring and it will be available on YouTube, is my understanding. If we don't have any more questions right now, Mattia promised he would introduce the next follow-up speaker in this series.
Yes.
And first of all, let's all thank Alain. I think we want to just thank you for this amazing talk. This is great and very inspiring as always. Thanks so much. A lot of applause here for you. And then maybe turning it over to Mattia for the final closure.
Yeah. Thank you, Alain, for such a great talk. And thank you, Alain, for coordinating. Thank you, everyone, for being here. So to conclude this, I wanted to share my screen and show you the flyer of the next talk, which you're going to see circulated on iMechanica LinkedIn. Right, so our next talk is going to be on machine learning application for solid mechanics, given by an early career researcher or a medium early career, Miguel Bessa in Brown University. Some of you probably know him already. He has been actually starting to do machine learning and mechanics before it was such a hot topic today. So he's going to be talking about uncertainty-aware application in AI for solid mechanics.
That's cool.
All right. So that's a good conclusion. And with that, and you're going to see this flyer again. Thank you, everyone. So to see you soon in a month.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye.
Bye.